The scientific measurements. We use measurements constantly in everyday life. Setting an alarm to know when to wake up, calculating how much rice to prepare for breakfast, counting out money for jeepney fare, weighing meat or fish at the market, or estimating the distance from your home to school. All of these rely on being able to describe things with numbers. But a number on its own is meaningless. A proper measurement always includes both a number and a unit, which tells you exactly what kind of quantity you are describing and what scale was used. For example, saying, "I bought 10" tells you nothing, but saying, "I bought 10 kilograms of rice" is clear, specific, and easy to understand. The right unit changes depending on what you are measuring. Measurements are the foundation of all scientific work. They give us consistent, reliable data to analyze results, compare observations, and draw fair conclusions from experiments. For science to work globally, researchers everywhere need to understand results in exactly the same way, so we need a shared, standard system. That agreed global standard is the International System of Units, usually shortened to SI. This is the modern, revised version of the metric system, formally established and adopted internationally in 1960. Almost every country in the world, including the Philippines, has officially adopted SI units for science, education, business, and daily use. Alongside the metric system, another set of units still used in some places is called the English system. Common units here include miles, yards, pounds, gallons, cups, pints, and tablespoons. This system has major drawbacks. Measuring tools and standards are not consistent everywhere. For example, the size of a tablespoon can vary from one household to another, so measurements often give inaccurate or uneven results. Values can also differ widely depending on where you live or what tools you use. By comparison, the metric system, or SI, is simpler, more convenient, and far more consistent. It uses prefixes based on powers of 10, making calculations and conversions straightforward. At its core are 7 fundamental SI base units, which describe basic physical quantities that cannot be broken down into simpler terms. All other SI units are built or derived from these 7. The 7 base units cover amount of substance, measured in moles with the symbol mole, electrical current, measured in amperes with the symbol A, length, measured in meters with the symbol M, luminous intensity, measured in candelas with the symbol CD, mass, measured in kilograms with the symbol kg, temperature, measured in Kelvin with the symbol K, and time, measured in seconds with the symbol S. Only 3 countries have not fully adopted the metric or SI system as their official standard: the United States, Liberia, and Myanmar. The Philippines officially uses SI units as required under Republic Act 9236, also known as the Philippine Standard Measurement System Act of 2003. Here we explore key physical quantities and how we measure them accurately. Mass is the total amount of matter that makes up an object. People often mix this up with weight, but they are not the same thing. Weight is the pull or force that gravity exerts on an object. Your mass stays exactly the same no matter where you are, but your weight changes if gravity changes. For example, an object would weigh much less on the moon than it does on Earth. Mass is one of the fundamental physical quantities, and its official SI unit is the kilogram. We measure mass using tools like digital balances, triple beam balances, or analytical balances. Length describes how long an object is, or the distance between 2 separate points. Its standard SI unit is the meter. You can use other related units for different scales: kilometers for very long distances, and centimeters for shorter lengths. Common tools for measuring length include rulers and tape measures. Volume is the total amount of 3-dimensional space that something takes up. The SI units for volume are the cubic meter and cubic centimeter. You will also often see liters or milliliters used. 1 cubic centimeter equals 1 milliliter, and 1 cubic meter equals 1,000 liters. You calculate volume in different ways depending on what you are measuring. For regular shaped solids, you can use math formulas. The volume of a cube is calculated by multiplying the length of one side by itself 3 times. For rectangular solids, multiply length by width by height, and for cylinders, multiply pi by the square of the radius by the height. For irregular shaped solids that you cannot measure with a formula, You use the water displacement method. First, measure the starting volume of water in a graduated cylinder, then carefully lower the object into the water. Record the new higher volume and subtract the starting number from the final number. The difference is the volume of the object. Liquids are measured directly with tools like graduated cylinders. Gases do not have a fixed volume on their own because their particles are spread far apart and they can be compressed easily. Building on what we learned about mass, length, and volume, let's now explore more key measurements and how we express them clearly and consistently. Density describes how tightly packed the matter inside an object is, or how much mass fits into a given amount of space. You calculate it using the formula D equals m divided by V, where D stands for density, m for mass, and V for volume. For objects with irregular shapes that you cannot measure with a simple formula, like a rough stone, you use the water displacement method to find its volume first. Using the example given, if a stone has a mass of 8 grams and a measured volume of 5 milliliters, its density works out to 1.6 grams per milliliter. Density also tells us whether something will float or sink. Pure water has a standard density of 1.00 grams per milliliter, so any object denser than water will sink, while anything less dense will float. SI prefixes are short labels we add to base units to make them easier to use for very large or very small values, based on powers of 10. For larger measurements, you use prefixes like tera for billions, giga for millions of millions, mega for millions, kilo for thousands, hecto for hundreds, and deca for tens. For smaller measurements, you use deci for tenths, centi for hundredths, milli for thousandths, micro for millionths, nano for billionths, and pico for trillionths. This system keeps numbers simple and avoids long strings of zeros. Temperature measures how hot or cold an object or substance is. The official SI unit for temperature is the Kelvin, which scientists use for precise calculations. You will also commonly see Celsius and Fahrenheit scales used for everyday weather and cooking, but these are not standard SI units. Finally, we use what are called derived quantities and derived units. These are not measured directly on their own, but are calculated by combining base units through multiplication or division. Area, for example, comes from multiplying length by width, so its unit is the square meter. Density comes from dividing mass by volume, so it is measured in kilograms per cubic meter or grams per cubic centimeter. Molar mass comes from dividing mass by the amount of substance, measured in kilograms per mole. Speed comes from dividing distance by time, measured in meters per second. Every derived unit is built from the 7 basic SI base units we covered earlier. Checkpoint. Let's review what we have covered so far with these quick questions. 1. What are the 7 fundamental quantities and their basic units? The 7 fundamental quantities and their official SI units are amount of substance, mole, electrical current, ampere, length, meter, luminous intensity, candela, mass, kilogram, temperature, Kelvin, time, second. 2. Differentiate fundamental quantities from derived quantities. Fundamental quantities are the basic, independent physical quantities that cannot be described using any other simpler quantities. They form the foundation of all other measurements. Derived quantities are calculated or created by combining 2 or more fundamental quantities using operations like multiplication or division. They depend entirely on base units to be defined. For example, length is a fundamental quantity, but area and speed are derived quantities.